Space extends without edges that can be reached, yet it is not without measure. Astronomers describe distance using light because light travels at a steady speed through empty space and provides a natural yardstick. A light year is the distance light covers in 1 year moving through vacuum without slowing. This unit does not describe time spent travelling by humans or machines, but it allows vast separations to be compared in a consistent way. When the night sky is observed, every point of light is seen not as it is now, but as it was when its light began the journey toward Earth. Distance and time are joined from the beginning. The observable universe has a finite size set by the age of cosmic expansion and the speed of light. There are regions so distant that their light has only just reached Earth, and regions even farther away whose light has not yet arrived. These limits define what can be seen, not necessarily what exists. Within this observable volume lie hundreds of billions of galaxies, each containing billions of stars. The distances between these galaxies are not fixed. Space itself expands, stretching the separation over time. On the larger scales, this expansion dominates motion, quietly carrying galaxies away from one another. Closer-in galaxies gather into groups and clusters where gravity overcomes expansion. The Milky Way belongs to a small collection of galaxies known as the local group. The distances here are still immense, measured in millions of light years, but they are small compared with the full observable span. Even within this local neighbourhood, the separation between stars is vast. The nearest star system beyond the Sun lies more than 4 light-years away, a gulf that dwarfs the scale of planets and orbits. Distance can also be described by the time it takes signals or spacecraft to cross it. A radio message sent from Earth reaches the Moon in a little more than 1 second. The same signal takes minutes to reach Mars when the planets are well aligned, and hours to reach the outer planets. These delays are not technical limitations. They are consequences of the finite speed of light. No improvement in engineering can reduce them. Every command sent to a distant probe, and every reply received is shaped by this unavoidable weight. Within the solar system, distances are often expressed in astronomical units defined by the average separation between Earth and the Sun. This scale feels large in daily life, yet it is small compared with the distances between stars. If the solar system were reduced to the size of a city, the nearest star would still lie far beyond the horizon. Space is mostly empty, and that emptiness sets the stage for how far humans might ever travel. The concept of travel implies movement through space over time. To understand possible reach distance must be paired with duration. Human lives are limited, and even extended lifetimes remain brief against cosmic scales. Machines can endure longer, but they too face wear damage and loss of power. Distance alone does not define reach. Reach emerges from the balance between how far there is to go and how long travellers can persist. Cosmic distances also differ in character depending on the region considered. Within a planetary system, paths curve under gravity, and motion follows predictable arcs. Between stars, trajectories are nearly straight crossing regions with almost no matter. Between galaxies, space expands, adding separation even as travellers move forward. Each layer introduces new challenges without changing the underlying fact that distance grows faster than human capability. The scale of the observable universe sets an upper bound on what could ever be reached even in principle. Regions beyond this horizon recede faster than light due to cosmic expansion, not because objects move through space at that speed, but because space itself stretches. No signal or traveller can overtake that expansion. Those regions are not just far, they're unreachable by any means allowed by known physics. Even within the observable boundary, the majority of galaxies are already moving away so quickly that reaching them would require travel faster than light relative to Earth. This is not permitted by current understanding of space and time. As the universe ages, more galaxies cross this threshold, slipping beyond reach without ever changing their local motion. The practical universe shrinks not because space contracts, but because time passes. The Milky Way itself offers a more modest arena. Its diameter spans about 100,000 light-years. From one edge to the other, light takes longer than recorded human history to travel. A spacecraft moving far slower than light would require spans of time that exceed not just individual lives but civilizations. The sheer size of a single galaxy already places strong limits on human travel. Distance is also felt through energy. To move faster requires more energy, and energy must be carried, generated, or collected along the way. Over cosmic distances, even small inefficiencies accumulate. A slight loss of speed or direction, trivial on short trips, becomes decisive over years and decades. Space offers little opportunity for correction without additional energy. Mapping distance is therefore an exercise in humility. Each layer outward reveals scales that grow beyond intuition. Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way drifts within the local group. The local group moves within larger structures shaped by gravity and expansion. At every step, the numbers increase and the meaning of travel changes. This outermost view does not yet answer how far humans could go. It establishes the terrain. It defines the arena within which all later questions must fit. Distance sets the boundaries before technology, biology, or ambition are considered. Any discussion of human travel through space begins here with the quiet fact that the universe is large, structured, and governed by limits that no desire can erase. Light sets the pace for everything that can carry information or influence across space. In a vacuum, light travels at a constant speed that does not depend on the motion of the source or the observer. This constancy is not a matter of engineering, but a property of space and time as described by modern physics. It is measured with high precision in laboratories and confirmed by many independent observations, from the timing of signals sent to spacecraft to the way starlight bends near massive bodies. Because light speed is the same for all observers, it becomes a boundary that reshapes the meaning of motion. When distances are small, the limit is not felt. When distances grow large, it becomes the central constraint on travel. Any object with mass requires more and more energy to increase its speed, and as it approaches light speed, the required energy grows without bound. In this framework, light speed is not just a high number. It is a barrier that cannot be crossed by pushing harder on ordinary matter. The limit also governs communication. A message to a distant craft cannot arrive sooner than light would. A reply cannot return sooner than another light speed interval. Across the solar system, these delays are measured in minutes and hours. Across interstellar distances, they are measured in years. Communication becomes less like conversation and more like a sequence of distant reports separated by long silences. No clever encoding can remove the waiting. Even if a craft were capable of travelling near light speed, it would still be constrained by the same limit for signals moving between it and Earth. The boundary appears in another way through causality, the rule that effects follow causes. In the modern description of space and time, events are linked by light cones regions that define what can influence what. A flash of light expands outward, and everything inside that expanding sphere can be affected by the flash. Anything outside it cannot be influenced yet. This structure is not an add-on. It is the core geometry of space-time. If a traveller could exceed light speed, then signals could be arranged in some frames of reference to arrive before they were sent, breaking the usual order of cause and effect. Physics does not treat this as a mere philosophical worry. It is a warning that the underlying equations and observed regularities would be violated. For known forms of matter and energy, the limit preserves a consistent ordering of events. When the question turns to how far humans could ever travel, the first consequence is straightforward. If travel is slower than light, then distance translates directly into time. A destination 4 light-years away cannot be reached in less than 4 years, as measured by clocks at rest relative to the departure point, even if a craft could travel at nearly light speed. If the craft travels much slower, the time stretches accordingly. A journey to the centre of the Milky Way, tens of thousands of light-years distant, becomes longer than any human lineage has existed. The scale of the galaxy alone makes much of it effectively inaccessible to travellers bound by a single lifetime, unless some way is found to greatly extend survival or to accept missions spanning many generations. Yet the light limit does not only create a simple conversion of distance into time, it also changes how time is experienced by a traveller moving very fast. As speed increases toward light speed, time dilation becomes significant. Time dilation is the slowing of a moving clock compared with a clock that remains behind. This is not an illusion caused by signal delays. It is a measurable difference in elapsed time. Experiments with fast-moving particles and precision clocks flown in aircraft and satellites confirm that moving clocks accumulate less time. At everyday speeds, the effect is tiny. At speeds close to light, it becomes large. For a traveller, this means that a long journey measured in years by distant observers could correspond to a shorter span of time experienced on board depending on the speed achieved. This does not remove the light speed barrier, but it alters the relationship between distance and personal duration. The same physics that enforces the limit also allows this shift in experienced time. A ship that could travel at a speed very close to light could in principle cross large distances within a human lifetime, as measured on the ship's own clocks while many more years pass on Earth. The traveller remains bound by biology, but biology is carried along a moving frame where time passes differently. This possibility is real in physics, but it carries a hidden cost. To reach such speeds requires extraordinary energy and control, and the environment outside the ship becomes more dangerous. Interstellar dust grains and gas atoms, harmless at low relative speeds, become high-energy projectiles. The ship must shield itself, and shielding adds mass, which makes acceleration harder. Another consequence of the light limit appears in the expanding universe. There are distant galaxies whose light reaches Earth now, but whose present-day distance is much larger than the distance implied by the age of that light. This is because space has expanded while the light travelled. For a traveller attempting to reach such a galaxy, the path is not through a static distance. The target keeps moving away as space stretches. For nearby structures like the local group gravity holds galaxies together, and expansion is not decisive. Beyond that, expansion becomes a rising tide. Some galaxies recede in such a way that even light emitted now will never reach Earth in the far future. These galaxies lie beyond a cosmic event horizon defined by expansion. They are part of the observable universe in the sense that ancient light from them is visible, yet they are not reachable by any traveller limited to light speed. The boundary of possible travel is therefore not simply the boundary of what can be seen. It is shaped by the changing geometry of space over time. Within the Milky Way, expansion is negligible, but the light limit still sets a harsh arithmetic. Even if a craft could cruise at 1/10 of light speed, a speed far beyond current human capability, for large vehicles the nearest star would still take decades to reach from the perspective of Earth. A trip across the galaxy would take hundreds of thousands of years, as measured by clocks at rest with respect to the galaxy. Time dilation would reduce the traveller's experienced time at higher speeds, but reaching those speeds pushes into the regime where energy demands, radiation hazards, and collision risks dominate. The light limit acts as a gatekeeper that forces any realistic plan to choose between slow travel that preserves engineering simplicity and fast travel that demands extreme solutions. The limit also shapes navigation and knowledge. A traveller far from Earth cannot rely on immediate updates or assistance. Any emergency unfolds faster than help can arrive. A ship becomes a closed decision-making system operating on its own information and predictions. Even the maps of space change slowly because distant stars are seen in the past. The traveller moves through a present that cannot be fully observed from afar in real time. Over interstellar distances, this separation between observation and reality becomes a practical constraint. Course corrections based on distant measurements must account for years of delay. No known material object can be accelerated through the light barrier. Light itself and other massless particles, if they exist, travel at light speed and cannot slow below it in a vacuum. Massive objects travel below it and cannot reach it. This division is built into the structure of relativity. It is not a preference, but a boundary expressed in the equations and supported by experiment. Some theoretical ideas propose ways around the barrier by altering space-time itself, but those ideas require conditions and forms of matter not demonstrated to exist in usable forms. When the focus is on what humans could ever do, the conservative boundary is the one supported by evidence travel remains at or below light speed, and practical travel remains far below it for large crews and life support. The outer layer of the problem is therefore set. The universe provides enormous distances, and physics provides a speed limit that turns those distances into time delay and isolation. Before a single engine is chosen, the possible destinations are already filtered by what light can connect. The next inward step is to see what it costs to approach the limit, not in dreams of breaking it, but in the real currency of energy and momentum that any moving mass must pay. Reaching far into space is never only a matter of direction. It is a matter of energy, because speed is purchased by energy and held against many forms of loss. Even in the emptiness between worlds, motion is not free. A spacecraft begins at rest relative to Earth's surface, already moving with Earth's rotation and orbit, and must change its velocity to leave to cruise and to arrive. Each change requires a push, and every push requires expelling reaction mass using external forces or converting stored energy into directed momentum. The farther the target, the more valuable speed becomes, yet speed becomes more expensive the faster it grows. At low speeds, increasing speed is intuitive. Doubling speed roughly quadruples kinetic energy, the energy of motion. That relationship already hints at rising costs. As a craft's speed climbs, the energy carried in its motion grows rapidly. If the craft must also slow down on arrival, that same energy must be removed or redirected, often requiring an equivalent expenditure. In deep space, there is no air to brake against, and gravity assists are only available near massive bodies. For most journeys, braking demands propulsion as much as acceleration does, doubling the energy burden. As speeds approach the speed of light, the energy cost rises far more sharply than the simple low-speed rule. Modern physics describes this with relativity, where momentum and energy include factors that increase steeply as speed nears light speed. The practical meaning is clear without equations. Each additional increment of speed near the limit costs more energy than the previous increment, and the cost escalates without bound. A massive ship can approach the limit but cannot reach it, because doing so would require infinite energy. The light barrier is therefore not only a rule about velocity, it is enforced by the energy accounting of the universe. Energy is not an abstract number in spaceflight. It must be carried as fuel stored as electricity harvested from sunlight, or produced by nuclear reactions. Each method has mass, volume, complexity, and failure modes. Chemical fuel stores energy in molecular bonds and releases it quickly, but the energy per unit mass is limited. Nuclear reactions store much more energy per unit mass, yet controlling them safely and converting their output to thrust is difficult. Electric propulsion uses electricity to accelerate propellant to high speeds, offering efficient use of mass, but it produces low thrust and requires long periods of operation. Light sails avoid carrying propellant by reflecting light, yet they rely on powerful light sources or long exposure to starlight, and they face challenges in steering and braking. Each approach is a trade between energy availability, thrust, and the mass that must be pushed. The cost of speed also appears in heat. Any engine that converts stored energy into motion produces waste heat. In space shedding, heat is hard because there is no air to carry it away. Heat must be radiated as infrared light from large surfaces. The more power a ship uses, the larger or hotter its radiators must be. High-power propulsion systems bring a quiet, persistent constraint. The ship must glow with its waste heat, and it must carry the structures needed to radiate that heat away. This increases mass and surface area, which can increase exposure to impacts and radiation. Beyond internal engineering, the external environment changes with speed. Interplanetary space contains a thin stream of particles from the Sun, along with dust and meteoroids. Interstellar space contains gas atoms and dust grains sparse but not absent. At low relative speeds, impacts are rare and mild. At high relative speeds, even a tiny particle carries a large amount of energy. A grain of dust smaller than a grain of sand can strike with the energy of a fast projectile if the ship is moving at a significant fraction of light speed. The ship must either avoid such grains through detection and maneuvering, or withstand them through shielding. Avoidance becomes hard because the grains are small and difficult to detect at long range. Shielding becomes heavy, and heavy shielding makes acceleration harder. This loop ties speed back to mass and energy again. Radiation also intensifies with speed. In the rest frame of the ship, particles and photons from ahead become blue shifted, meaning their wavelengths compress and their energies rise. Background radiation that is harmless at low speeds can become more penetrating at high speeds. The interstellar medium, though thin, becomes a source of continual impacts by high-energy atoms. These impacts can produce secondary radiation within shielding materials. Protecting humans under these conditions demands careful material choice and thickness, which again adds mass. The energy required for high-speed travel grows with the mass being carried. A crewed ship carries not just people, but air, water, food, living space, medical supplies, redundancy and shielding. These needs multiply the mass compared with an uncrewed probe. As mass grows, the energy required for any given speed grows proportionally, and the difficulty of carrying or generating that energy grows faster, because the systems that provide energy also have mass. This coupling is one of the central reasons why uncrewed missions push outward first. Machines can be small and hardy. Human missions require a moving habitat. Practical space travel therefore unfolds in layers of compromise. For short trips, speed is limited by the gravity well of Earth, and by propulsion that can provide enough thrust to leave quickly. For longer trips, such as to the outer solar system, speed is limited by the amount of propellant that can be carried, and by the length of time engines can run. For interstellar travel, speed becomes a defining question, because the distances are so large that slow travel stretches into centuries. Yet pushing speed up toward even a small fraction of light speed brings the energy and shielding problems into focus. There is also a distinction between energy and power. Energy is the total budget required to change velocity and sustain systems. Power is how quickly energy is used. A ship can carry a large amount of energy, but release it slowly, producing low thrust over long times. This is the pattern of electric propulsion, where efficient engines run for months or years, steadily building speed. Alternatively, a ship can release energy rapidly, producing high thrust for a short time, as chemical rockets do. For interstellar travel, high final speeds require enormous energy, and achieving them within a reasonable time often requires high power, which intensifies heat rejection and system stress. Even if a ship could acquire the necessary energy, the direction of thrust matters. For a journey to a distant star, a ship must accelerate for part of the trip, and decelerate for part of the trip if it intends to arrive with control. If it accelerates halfway and decelerates halfway, it minimizes total travel time for a given maximum acceleration. This strategy, however, demands that the ship carry propellant, or use an external beam both for speeding up and for slowing down. Without braking, a fast ship becomes a flyby mission, passing the target at high speed with only brief observation time. For humans aiming to stop and live near another star, braking is not optional. It is a second full price tag attached to the first. The rise of energy cost with speed sets a practical horizon. The universe allows near-light travel in principle, but the energy demanded for large shielded crewed vehicles grows beyond what is likely to be gathered and managed by any near-term civilization. That does not mean travel beyond the solar system is impossible. It means that any such travel will likely proceed at speeds far below light speed, unless entirely new evidence-supported methods of producing thrust and managing impacts emerge. In the real accounting of physics, distance is paid for with time when energy cannot be paid in sufficient quantity. This region of the problem remains external, concerned with motion, fuel, heat, and the space environment. The next inward step is to see how time itself, as measured by different clocks, shapes what travel means for those who leave and those who remain, and why the same journey can have two different durations depending on the frame in which it is measured. Time becomes the quiet currency of space travel once distance and speed are fixed by physics and engineering. For journeys beyond the immediate neighbourhood of Earth, the limiting factor is rarely a single mechanical threshold. It is the duration required to cross the gap while maintaining life function and purpose. Time is measured by clocks, and clocks are not all equivalent when motion becomes extreme. Modern physics describes time and space as intertwined, so that how time passes depends on speed and gravity. This dependence is small for ordinary travel, but it grows as speed increases and as journeys extend. For the question of how far humans could ever travel, time is not a side detail. It is the shape of the whole problem. In everyday experience, time feels universal. 1 second follows the next in the same way for everyone. In spaceflight, even within the solar system, small differences appear. Satellites in orbit experience time slightly differently from clocks on the ground because they move quickly and sit higher in Earth's gravitational field. These effects are measured and corrected in navigation systems. The corrections are not optional. Without them, positioning errors accumulate. This practical need confirms that time does not pass at exactly the same rate in all conditions. Two main effects matter: time dilation from speed and time dilation from gravity. Speed time dilation means that a clock moving relative to an observer ticks more slowly than the observer's clock. Gravity time dilation means that a clock deeper in a gravitational field ticks more slowly than a clock higher up. For most of human history, these were curiosities. For high-speed travel, speed time dilation becomes the dominant effect. It changes the relationship between the duration experienced by travellers and the duration measured by those who remain behind. Consider a craft that travels steadily through deep space at a speed that is a significant fraction of light speed. From the perspective of Earth, the craft's clocks run slower. The crew experiences fewer days and years than Earth does during the journey. If the craft could reach extremely high speed, the crew could in principle cross a large fraction of the galaxy within a lifetime on board, while many lifetimes pass on Earth. This does not allow the craft to outrun light. Signals still require at least the light travel time, and the craft still cannot arrive sooner than light would in Earth's frame. Yet the craft's own experience time can be much shorter than the Earth frame travel time. This possibility leads to a subtle distinction. When speaking about how far humans could travel, there are two clocks to consider. One is the clock of the departure society, the time that passes for those who remain. The other is the clock carried by the travellers, the time that passes in their bodies and minds. A destination that is effectively unreachable within the first clock might be reachable within the second if speed is high enough. But reaching the high speed brings the energy shielding and impact problems inward from earlier considerations. Time dilation is not a free gift. It is linked to the very speeds that are hardest to achieve safely. There is also an asymmetry that cannot be avoided. If a crew leaves Earth, travels at high speed and returns, they come back to a future in which more time has passed for everyone else. This is not a paradox in the practical sense. It is a consequence of different paths through space-time. The traveller's world line, the path of their life through time and space, includes high-speed segments that reduce their accumulated time compared with those who stay near Earth. The effect has been tested with clocks and with particles that live longer when moving fast. It is a stable feature of the best-tested physics available. For one-way interstellar travel, the asymmetry becomes a separation rather than a reunion. Even if a crew experiences only decades on board Earth may experience centuries. The society that launched the mission may change beyond recognition. Institutions may vanish. Languages may shift. The very reasons for the journey may fade. This is not a statement of meaning or purpose. It is logistical reality. Long travel times sever continuity. They also change how support can be provided. A mission cannot rely on resupply rescue or rapid instruction when the communication delay is years and the departure world evolves independently. Time also sets limits through biology. Human bodies age. They require continuous repair at the cellular level. Even with good health and medical care, there are constraints on how long an individual can remain functional. If travel is slow, the mission must either accept that the original crew will not arrive, or must rely on reproductive continuity and training across generations. Alternatively, the mission might attempt to slow biological processes by cooling or other forms of metabolic reduction, but long-term safe methods for this in humans are not established as a reliable technology for spaceflight. Without such methods, time becomes a strict wall. Even within a single lifetime, time brings exposure. Radiation dose accumulates with duration. Small failures accumulate with duration. Psychological strain accumulates with duration. Microgravity effects accumulate with duration unless countermeasures are used. For a long journey, the ship must not merely function. It must function reliably for years or decades without external repair infrastructure. Time multiplies every risk. A risk that is acceptable for a week may be unacceptable for a decade. The way time is counted also matters for planning. In the Solar System mission, designers use ephemerids, precise models of planetary positions to plan trajectories. These models remain accurate over years, but must include perturbations, small gravitational tugs, and relativistic corrections. Over interstellar timescales, the positions of stars change. Stars orbit within the galaxy, and their relative distances shift. A target that is 4 light-years away today will not be in exactly the same direction and distance decades later. Navigation must therefore include continual measurement and adjustment. These adjustments are not a severe burden at low speeds over short trips, but over long durations they become essential. Time introduces drift. Drift introduces the need for correction. Correction requires energy and propulsion reserves. There is another time-related effect that appears once a ship moves very fast. The appearance of the outside world changes. Light from ahead becomes concentrated and shifted toward higher energies, while light from behind becomes stretched to lower energies. The sky becomes anisotropic, brighter ahead, and dimmer behind. This is a consequence of relativistic beaming and Doppler shift. For a crew, it would change the environment of observation and could affect shielding requirements because high-energy photons become more penetrating. These are not aesthetic changes. They are operational because sensors and radiators interact with the radiation field around the ship. As speed rises, the ship's relationship with ambient light and particles is altered by time and motion together. For most realistic human travel scenarios, speeds remain far below light speed because of the energy and shielding costs. In that regime, time dilation is small, and the 2-clock ship time and Earth time remain nearly the same. The journey then becomes a direct test of endurance across ordinary time. A trip to the nearest stars becomes measured in decades or centuries for everyone, not just for those left behind. This is where time becomes the defining barrier. It is not that the distance is conceptually impossible. It is that the time required is longer than the stable lifespan of systems, institutions, and often individuals. The region of the problem therefore narrows from the outer geometry of space to the inner arithmetic of lived duration. Time dictates whether travel is exploration by a single crew, by a lineage of crews, or by machines. It dictates whether destinations are meaningful in terms of arrival, or only in terms of passing by. It dictates whether communication remains a useful feedback loop, or becomes a one-way archival record. Having established how time changes with motion, and how time accumulates as a risk, the next inward layer is the practical act of escaping Earth itself, because every outward journey begins in the deep gravity well of a planet, where the first and most immediate cost is not distance, but the energy required simply to leave the surface behind. Every path into deep space begins with a local problem that is easy to overlook when thinking about stars and galaxies. The first barrier is gravity, because a planet holds tightly to anything near its surface. Earth's gravity well is deep, and climbing out of it requires a large change in velocity delivered in a short time. This requirement shapes the design of launch systems, the mass that can be carried, and the kinds of missions that can be attempted. Before interplanetary distances are considered, the immediate question is how to lift a payload from ground level to a place where it can orbit, maneuver, and depart. On Earth, weight is the constant force that must be countered. A rocket must produce thrust greater than its weight to rise. It must do so while carrying its own fuel, and most of its starting mass is propellant. Chemical rockets remain the main method because they can deliver high thrust, meaning a strong push, over minutes, not months. High thrust is essential for launch because lingering near the surface consumes fuel while fighting gravity. This is known as gravity loss, where fuel is spent merely to avoid falling rather than to build useful speed. A rocket that accelerates slowly from the surface wastes much of its propellant. The concept of escape velocity expresses the minimum speed needed to leave Earth's gravity without further propulsion, ignoring atmospheric drag and assuming the craft starts far from the atmosphere. In practice, real departures do not occur as a single jump to escape speed. Spacecraft usually reach orbit first. Orbit is a form of falling around Earth where forward speed is high enough that the curved path of free fall matches Earth's curvature. Achieving orbit requires a large horizontal velocity, and this becomes the primary requirement for space access. Once in orbit, a spacecraft is already moving quickly around Earth, and leaving for other destinations becomes a matter of adding more velocity in the right direction. The climb out of the gravity well is therefore achieved step by step first, by reaching orbit, then by raising the orbit, and then by departing. The atmosphere adds another layer. Air resists motion and heats vehicles through friction and compression. During ascent, rockets must push through dense air while keeping structural loads and heating within limits. During return, spacecraft must survive intense heating and deceleration. The presence of atmosphere shapes not just launch, but the entire life cycle of missions. It demands heat shields, careful trajectories, and for crewed vehicles reliable ways to manage high accelerations and emergency scenarios. The mass penalties imposed by launch are severe. Every kilogram placed in orbit requires many kilograms of propellant at liftoff. This cascading requirement means that heavy, well-shielded, long-duration habitats are hard to launch in one piece. Instead, human spaceflight has relied on assembling structures in orbit, using multiple launches to build a station or a vehicle. This approach spreads risk and cost, but introduces complexity. Assembly requires docking alignment and maintenance, and it depends on the reliability of multiple launch events. For deep space missions, the need for many launches becomes a major constraint. It is not simply a matter of building a ship. It is a matter of delivering its mass to orbit without losing it to the unforgiving arithmetic of rockets. The rocket equation expressed in engineering terms explains why launch is so mass-sensitive. It links the change in velocity a rocket can provide to the speed at which it can eject propellant and to the ratio between its initial and final mass. In plain terms, if the propellant exhaust leaves the engine faster, the rocket can gain more speed for the same amount of propellant. If the rocket carries more propellant relative to its dry mass, it can also gain more speed. But propellant tanks, engines and structure add dry mass, and adding dry mass makes it harder to carry enough propellant. The equation creates a strong incentive to make everything light. Yet crewed missions also demand redundancy shielding and robust systems which tend to add mass. The result is a persistent tension between safety and reach. Earth's gravity also imposes constraints on propulsion choices. Electric propulsion can be very efficient in how it uses propellant, but it produces low thrust. It is not suited to lifting off from Earth. Nuclear thermal concepts could in principle provide higher performance than chemical rockets for in-space stages, but launching such systems from Earth raises safety, regulatory and engineering concerns. In practice, high-thrust chemical rockets remain the workhorse for leaving the ground, while other propulsion types are better suited once a spacecraft is already in space. This division means that the first stage of any deep space human travel plan is likely to remain constrained by chemical launch, or by some other high-thrust method that can operate in atmosphere. There are also environmental and operational limits. Launch windows depend on weather range safety and orbital mechanics. A mission to deep space requires precise timing because departing from Earth to reach another planet or trajectory efficiently depends on relative positions. Even for leaving Earth entirely, launch timing affects the inclination and energy of the resulting orbit. If a crewed vehicle must be assembled in orbit, then each launch must align with the orbital plane and rendezvous opportunities of the assembly site. These timing constraints can stretch preparation over months, increasing risk and cost. Once a spacecraft is in orbit, it gains freedom that is absent on the ground. It is already above most atmospheric drag, and it can use small continuous thrust over long times if desired. Yet orbit is not a safe harbour by default. Low Earth orbit still lies within Earth's magnetosphere, and within a region of debris created by decades of launches. Debris travels at high relative speed, and small fragments can damage spacecraft. For long-term assembly and departure, debris avoidance and shielding become concerns. Even before leaving Earth, the environment around Earth introduces hazards that must be managed. To depart for deep space, a spacecraft must increase its orbital energy. This is often done by firing engines at specific points in orbit, using the fact that changes in velocity have different effects depending on where they are applied. A burn performed at the lowest point of an orbit can raise the highest point more efficiently, and repeated burns can gradually lift a craft into higher orbits. For missions to the Moon, or beyond the final step, is a burn that places the craft on a trajectory that escapes Earth's gravity or reaches a transfer path. Each of these steps requires propellant and careful planning. The gravity well matters again for returning. A mission that takes humans far away must plan not only to leave, but also to come back unless it is explicitly one way. Return requires enough propellant for course corrections, and for Earth re-entry systems that can survive the heat and deceleration. The need for return capability increases mass, which increases launch requirements, which increases cost and complexity. This feedback loop pushes some concepts toward one-way travel as distance increases, but one-way human travel introduces profound logistical demands in life support and long-term habitability. The climb from Earth's surface is therefore a gate that filters possibilities. It makes large interstellar ships hard to begin, not only because of their eventual travel needs, but because of the difficulty of building and fueling them in space in the first place. It encourages stepwise expansion, where humans first learn to live in orbit, then to travel to nearby worlds, and only then to consider more distant journeys. With the vehicle free of Earth's immediate grip, The next outward motion becomes a matter of moving through the solar system where gravity still shapes every path, but no longer holds travellers to a single world. The next inward layer of the question therefore turns to the solar system as the first true arena of travel where reachable distances are measured in days, months, and years, and where the practical horizons of human missions can be examined without leaving the neighbourhood of the Sun. Within the solar system, travel becomes less like climbing and more like sliding along invisible tracks. These tracks are orbits shaped by gravity and inertia. A spacecraft does not simply point at a planet and fly straight there. It shares the Sun's gravitational field with every planet, and it begins with the velocity of Earth in its orbit. To go elsewhere, it must change that velocity by a controlled amount, and at a controlled time. This is why interplanetary travel is often described in terms of transfers where the spacecraft moves from one orbit around the Sun to another. The distances are large, but the more immediate challenge is matching speed and direction with a moving target. Planets are not stationary destinations. They move around the Sun at different speeds and at different distances. A mission to Mars is easiest when Earth and Mars are positioned so that a spacecraft can depart Earth and arrive at Mars as Mars reaches the intercept point. These alignments occur on a repeating cycle. The resulting launch windows set a cadence for missions. When the window is favourable, a spacecraft can travel on a path that uses relatively little propellant at the cost of taking months to arrive. When the window is less favourable, a faster trip may be possible but demands much more energy. The trade between time and propellant is present even within the solar system, though the timescales remain within human planning. A common low-energy route between two circular orbits is a Hohmann transfer, a path that touches the departure orbit at one end and the destination orbit at the other, with an elliptical arc between. It is efficient in propellant because it uses two main velocity changes, one to leave the initial orbit and one to match the final orbit. Its cost is time. The spacecraft follows the ellipse at a pace set by gravity, not by the impatience of travellers. For Mars, such a transfer typically takes many months depending on the exact geometry of the launch. For the outer planets, transfer times stretch into years. Faster transfers exist. A spacecraft can take a more direct path with a higher departure speed, reaching the destination sooner, yet the energy required rises quickly. The earlier discussion of kinetic energy applies here in a practical way. Cut in travel time is not simply a scheduling choice. It increases propellant needs, engine requirements, and heat and stress on the vehicle. For crewed missions, higher speeds also tend to raise exposure to radiation and micrometeoroid impacts per unit time, because the spacecraft spends less time in transit, but may require trajectories that pass through harsher regions, or demand higher energy propulsion systems with associated mass and complexity. The solar system offers no simple way to have both fast and easy travel with current technology. Gravity assists provide an additional tool. By passing near a planet, a spacecraft can exchange momentum with that planet's motion around the Sun. The spacecraft leaves the encounter with a different speed and direction relative to the Sun without expending propellant for the full change. This technique has allowed uncrewed probes to reach the outer solar system and beyond with limited onboard fuel. Gravity assists are not free. They require precise targeting, they depend on planetary positions, and they often lengthen the route. For human travel, the longer time may be unacceptable, and the close passes near planets can involve higher radiation environments or other hazards. Still, the method illustrates a broader truth within the solar system. Gravity is both obstacle and engine. Human travel times in the solar system are constrained not only by propulsion, but by life support and radiation. Beyond low Earth orbit, astronauts leave the protection of Earth's magnetic field and encounter a harsher radiation environment. The Moon lies close enough that a crew can reach it in a few days, limiting total exposure. Mars lies much farther. Even a relatively direct trip involves months in interplanetary space where cosmic rays and solar energetic particles contribute to accumulated dose. Shielding can reduce dose but adds mass, and mass is costly to launch and accelerate. Mission planning must therefore balance trajectory shielding and acceptable exposure levels. Another constraint is the need for reliable systems over duration. A journey to the Moon can rely on supplies and redundancy for days. A journey to Mars must sustain air, water, and power for many months. If a failure occurs, immediate rescue is not possible. The spacecraft and crew must be able to diagnose and repair problems with onboard tools and spares. This pushes designs toward robustness and redundancy, again increasing mass. It also shapes operational choices such as the selection of transfer orbits that allow abort options where a spacecraft can return to Earth without complex maneuvers if something goes wrong early in the mission. These options are valuable for safety, but may constrain launch timing and increase travel time. Within the solar system, the time required for travel also affects human physiology and psychology. Microgravity weakens bones and muscles and alters fluids in the body. Countermeasures such as exercise help, but do not fully remove the effects. Long travel times therefore demand larger spacecraft with room for exercise and possibly rotating habitats that create artificial gravity through spin, though such designs have not yet been used for human missions and would introduce engineering challenges in stability and docking. Time also affects mental health. Months in confined space with limited privacy and delayed communication place demands on crew selection training and onboard routines. These are not secondary issues. They can determine mission viability. The practical horizon for repeated human travel in the solar system is shaped by these combined constraints. The Moon is within reach with current or near-term systems, and it serves as a testing ground for long-duration habitation and operations beyond Earth's atmosphere. Mars is a more difficult step, requiring interplanetary transit times that expose crews to deep space conditions and demand high reliability. Beyond Mars, human travel becomes increasingly challenging. The asteroid belt lies farther still, and the outer planets are so distant that travel times become many years with conventional propulsion. The radiation dose and system reliability demands would rise, and the return would be prolonged. For uncrewed missions, these barriers are less severe. Robots can hibernate, tolerate higher radiation, and operate with delayed commands. They can take slow gravity-assist trajectories that would be impractical for humans. As a result, much of what is known about the outer solar system comes from robotic exploration. This difference underscores a pattern that likely persists. Machines extend reach long before humans follow. Human travel is constrained by the needs of a living organism and by the requirement to return or to build a new habitat on arrival. Even within the solar system, there is a clear boundary between travel that is routine and travel that is exceptional. Routine travel requires vehicles that can be built, launched, and operated repeatedly with manageable risk. Exceptional travel may be possible once at great cost and with high risk, but cannot become a stable practice. When considering how far humans could ever travel, the distinction matters because the ultimate horizon is influenced not by a single heroic mission, but by what can be sustained as a long-term capability. The solar system is the arena where sustainability can be tested. This region remains largely external, dealing with trajectories, transfer, times, gravity assists, and mission reliability. The next inward step is to examine propulsion systems more directly, not as abstract ideas, but as families of technology that have been built, tested, or are grounded in known physics. From that foundation, it becomes possible to see how much speed and range each family can plausibly provide, and where the boundaries appear when human crews and their required habitats are included. Propulsion determines not only where a spacecraft can go, but how it can live along the way. Different propulsion families trade thrust efficiency, complexity, and resource needs. Thrust is the immediate pushing force that changes speed quickly. Efficiency in practical terms is how much change in velocity can be gained from a given mass of propellant. A system can be efficient yet weak, delivering a gentle push over months, or strong yet wasteful, delivering a hard push over minutes. Human travel demands both strong thrust at launch and escape, and efficient propulsion for long journeys, where carrying enormous propellant mass becomes impractical. The existing landscape of propulsion shows why the solar system is accessible, while interstellar travel remains far beyond present capability. Chemical rockets are the most familiar family. They burn fuel and oxidizer, producing hot gases that expand through a nozzle and create thrust. Their strength is high thrust and proven reliability. Their limitation is modest exhaust speed because chemical reactions release a limited amount of energy per unit mass. This confines the maximum change in velocity obtainable without carrying prohibitive propellant. Chemical propulsion excels for launching from planets and for rapid maneuvers, but it does not scale well to interstellar speeds for large payloads. For crewed missions within the solar system, chemical propulsion remains central for launch and for major trajectory changes. Electric propulsion is a broad family that uses electricity to accelerate propellant, often ions, to very high exhaust speeds. Higher exhaust speed means better efficiency in propellant use, allowing larger cumulative velocity changes with less propellant mass. The cost is low thrust. Electric engines push gently, so they must operate for long periods. They are valuable for uncrewed spacecraft that can spend months spiraling outward from Earth orbit and gradually building speed. For human travel, electric propulsion can be useful for cargo and for slow transfers, but the low thrust makes it hard to shorten travel time, to reduce radiation exposure and life support burden. Electric propulsion also requires substantial electrical power. Near the sun, solar panels can provide power, but farther out sunlight weakens and panels must grow large. Nuclear power sources can provide steady electricity, but integrating them with crewed vehicles introduces mass and safety challenges. Nuclear thermal propulsion is a concept grounded in known physics, where a nuclear reactor heats a propellant such as hydrogen and expels it through a nozzle. Because nuclear energy is far denser than chemical energy, the exhaust can reach higher temperatures and speeds than chemical rockets can manage, improving efficiency while still providing relatively high thrust. This makes nuclear thermal propulsion attractive for human missions to Mars because it could reduce travel time or propellant needs compared with chemical stages. The challenges lie in building a reactor that is lightweight, reliable and safe, and in managing radiation and heat. The reactor must operate in space without contaminating the crew or Earth, and its materials must withstand high temperatures. Although ground tests of nuclear thermal engines have occurred historically, no such system has yet flown with humans. The concept remains plausible, but not yet proven as an operational capability. Nuclear electric propulsion combines a nuclear power source with electric engines. A reactor generates electricity which powers high-efficiency thrusters. This can deliver large cumulative velocity changes over long durations, potentially useful for deep space cargo and for some crewed missions if radiation shielding and heat rejection can be managed. The key constraint is power density, the amount of electrical power per unit mass of the system. Higher power allows higher thrust shortening trip times. Lower power forces long spirals and long cruises. Radiators become large because waste heat from the reactor and power conversion must be shed to space. For crewed missions, the reactor must be placed at a distance or shielded heavily again, adding mass and structural complexity. Solar sails use the momentum carried by light. Photons have no mass, yet they carry momentum, and when reflected they impart a small push. A large lightweight sail can therefore accelerate without carrying propellant. The acceleration is gentle, and it decreases with distance from the Sun as sunlight weakens. Solar sailing is most promising for small probes and for missions that can accept long acceleration times. For human travel, the sail area required would be enormous and controlling, and deploying such a structure would be challenging. Still, the idea demonstrates a path around propellant limitations using external energy sources rather than carrying all energy on board. Beamed propulsion extends this concept. Instead of relying on sunlight, an external laser or microwave beam pushes a sail or heats a propellant stream. In principle, this could provide higher acceleration and higher final speeds without the vehicle carrying its own energy source. The limitations are practical and severe. The beam must remain tightly aimed over vast distances requiring large optics and precise tracking. The power levels would be enormous for any substantial payload. The infrastructure must be built and maintained likely far from Earth's atmosphere. Braking at the destination is also difficult unless a second beam source exists there, or the craft carries a braking system. These challenges do not violate physics, but they shift the problem from building a ship to building a vast energy and optics infrastructure, and they raise questions about reliability across decades. Another proposed family is fusion propulsion, which would use fusion reactions to release energy and produce thrust. Fusion is well understood as a process in stars and in experimental reactors on Earth, but controlled fusion for power generation remains an engineering challenge, and converting fusion output into a compact rocket system adds additional difficulty. Fusion offers high energy per unit mass, and could in principle support higher exhaust speeds than chemical or nuclear thermal systems, enabling faster travel. The uncertainty lies not in the physics of fusion, but in the feasibility of a practical, lightweight, reliable fusion engine with adequate shielding and waste heat management. Without such an engine, demonstrated fusion remains a possibility rather than an established pathway. Antimatter propulsion is sometimes discussed because matter-antimatter annihilation releases energy with extremely high density. Yet antimatter is difficult to produce, store, and handle. Production requires enormous energy input, and storage requires fields that prevent contact with normal matter. Even small amounts pose severe safety risks. In the context of realistic human travel, antimatter is not a near-term or well-supported solution. It illustrates the extreme end of the NG scale, showing that high speeds demand exotic resources. Across all these families, the basic trade persists. To travel far within limited time, high speed is needed. High speed demands high energy. High energy systems bring heat radiation and mass. Mass drives up required propellant or power. The loop tightens most sharply for crewed ships where the payload includes a life support environment and shielding. Uncrewed probes can exploit low-thrust efficient propulsion over long durations, and they can accept flybys without braking. Crewed missions generally need higher thrust and the ability to arrive with control. This propulsion landscape suggests a layered future of reach. Within the solar system, combinations of chemical propulsion for launch and possibly nuclear thermal or high-power electric systems for interplanetary legs could extend human presence to the Moon and Mars, and perhaps to some near-Earth asteroids. Beyond that, the times and energies required rise steeply. Interstellar travel would require either extremely long-duration missions at modest speeds or propulsion approaches that deliver far higher speeds than current systems can provide, likely relying on large-scale infrastructure or breakthroughs in power density and materials. The journey inward now turns from propulsion types to the fundamental mass constraint that links them all. The same engine behaves very differently depending on how much mass it must move, and space travel imposes a compounding penalty, where added mass demands added propellant, which itself adds mass. Understanding this compounding effect is essential for judging any claim about how far humans could ever travel, because it explains why small probes can roam far while crewed ships remain close to home. Mass is the silent weight of every space mission, even where weightlessness is felt. A spacecraft in orbit is in free fall, yet its mass still determines how much force is needed to change its motion. Every engine, no matter how advanced, must obey momentum conservation. To accelerate a vehicle, something must be pushed backward. In most practical systems, that something is propellant expelled at high speed. The relationship between propellant exhaust speed and achievable change in velocity creates a compounding constraint. This constraint is often summarized by the rocket equation, but its meaning can be expressed in everyday terms. If a vehicle needs a large change in velocity, it must either throw propellant backward very fast or carry a great deal of propellant. If it carries more propellant, it becomes heavier, and accelerating that added propellant requires even more propellant. The mass of fuel becomes both solution and burden. This compounding effect is why rockets look the way they do with large tanks and relatively small payloads. At liftoff, most of the mass is propellant. As propellant is burned, the vehicle becomes lighter, and the same engines can accelerate it more effectively. Staging takes advantage of this. By dropping empty tanks and engines, a rocket sheds dead mass, improving the ability of the remaining stages to accelerate. Staging is not a convenience. It is a direct response to the exponential penalty created by needing large velocity changes with limited exhaust speed. In deep space, the same logic continues even when staging is no longer possible or desirable. A crewed ship that must accelerate to high speed and then decelerate must carry propellant for both phases unless it uses external forces such as beamed propulsion or gravitational braking. Carrying propellant for deceleration means carrying propellant that must itself be accelerated during the outbound burn. This makes the initial mass larger than it would be for a one-way flyby probe. If the mission also aims to return to Earth, it must carry or preposition additional propellant, for the return multiplying the mass again. This is why return missions to distant targets are so difficult. Each layer of required capability adds mass, and mass increases the propellant burden in a non-linear way. The exhaust speed of an engine is therefore crucial. Engines that eject propellant at higher speed can achieve a given change in velocity with a smaller propellant fraction. Electric propulsion achieves very high exhaust speeds, which is why it can deliver large cumulative velocity changes with modest propellant. Yet electric propulsion produces low thrust, so the journey takes longer. For human travel, longer time increases life support, mass radiation exposure, and system reliability demands. Thus, improving exhaust speed solves one problem while intensifying others. The mass constraint does not vanish. It moves. Crew mass is not just the mass of bodies. A crew requires a pressurized habitat shielding water, food waste processing, medical capability, thermal control, and redundancy. Each of these adds structure, equipment, and supplies. Even if some supplies can be recycled, the recycling systems themselves have mass and require power. Radiation shielding is especially heavy if done with dense materials, and even lighter shielding with water or plastic still adds substantial mass. Every kilogram added for safety and comfort is a kilogram that must be launched from Earth and accelerated through space. One response is to shrink the crewed vehicle and accept greater hardship, but there are limits. Humans require a minimum volume for health and operations, and missions lasting months or years require space for movement, work, and rest. Very tight confinement increases psychological stress and limits exercise options, worsening physical decline in microgravity. Reducing shielding increases radiation dose and raises long-term health risks. Reducing redundancy increases the chance that a single failure ends the mission. These are not abstract risks. They are the central design drivers for long-duration human missions. Mass is therefore tied directly to survivability. Another response is to separate cargo from crew. Heavy items such as habitat modules, supplies and propellant can be sent ahead using slow but efficient propulsion, while a smaller crew vehicle follows on a faster trajectory. This concept reduces the mass that must be accelerated, quickly easing the propellant burden for the crewed segment. It also adds complexity because prepositioned cargo must arrive reliably, remain functional until the crew arrives, and be accessible at the destination. If any critical element fails, the crew may face an impossible situation. The approach can extend reach within the solar system, but it depends on a robust supporting infrastructure and reliable autonomous systems. Mass constraints also shape the idea of in-space refueling. If propellant can be produced or stored in orbit, vehicles can depart with full tanks without carrying the propellant up from Earth in a single launch. This spreads the lifting burden across many launches and can allow larger missions. It also opens the possibility of using resources from the Moon or asteroids to produce propellant-reducing dependence on Earth. Yet resource extraction and processing require equipment, power and maintenance, all of which must be delivered and operated. Building such infrastructure is itself a mass-intensive project. It may be possible over decades, but it is a long path. For the question of ultimate human reach, such infrastructure could gradually move the staging point outward, making deeper missions more feasible without changing the fundamental physics. For interstellar travel, the mass problem becomes extreme. To reach even a small fraction of light speed with a crewed habitat, the kinetic energy involved is enormous. If the propulsion uses onboard propellant, the propellant mass required can become overwhelmingly large unless exhaust speed is also extremely high. High exhaust speed implies high-energy propulsion, such as advanced nuclear or fusion concepts, which then require heavy shielding and radiators. If the mission aims to brake at the destination, the required propellant doubles in effect. If it aims to return, it multiplies again. The compounding mass penalty can quickly exceed any plausible launch and assembly capability. This is why many interstellar concepts focus on small probes rather than people. Small probes can be accelerated by external beams or carry limited propulsion, and they can accept flyby encounters. Humans cannot easily accept these compromises. Even within the solar system, mass limitations dictate mission architecture. The difference between a crewed flyby of Mars and a crewed landing is largely a mass difference. Landing requires carrying descent systems, landing fuel surface habitats and descent fuel. Each of these must be launched from Earth or produced elsewhere. The mass climbs steeply and with it the complexity. For deeper destinations, similar multiplier appear. A crewed mission to the moons of Jupiter would face long travel times and intense radiation near the planet demanding heavy shielding. A crewed landing on an outer moon would require ascent and descent systems in addition to deep space transit systems. Mass becomes a barrier long before distance becomes a barrier. The mass constraint also interacts with reliability. Redundancy improves safety but adds mass. Repair capability improves endurance but adds mass. Long missions demand both. Over time, even small failure rates accumulate. A system that has a 1% chance of failure per month becomes highly risky over many years. To reduce risk, designers add backup spares and robust components, all of which add mass. The mass penalty is therefore not only about propulsion, it is about engineering for longevity. This region of the problem reveals why claims of far human travel often collapse under accounting. If a proposal does not address the compounding mass of propellant shielding and life support, it is incomplete. Yet mass does not only constrain, it also points towards solutions. If mass can be reduced through better materials, more compact life support, or effective recycling, then reach improves. If propellant can be obtained away from Earth, then the initial mass at launch can be reduced. If external energy can accelerate a vehicle without onboard propellant, then the compounding effect can be weakened. These are directions for progress, but each requires large-scale development and careful testing. Having traced how mass amplifies every demand, the next inward step is to turn fully toward the living core of human travel. Even if propulsion and mass constraints could be managed, a crew remains a biological system that must maintain air, water, food, and stable conditions for years. The ship becomes an ecosystem in miniature, and its limits may define human reach as strongly as physics does. A crewed spacecraft is not only a vehicle, it is a closed environment that must keep living bodies stable, while the outside offers almost nothing to support them. In deep space there is no breathable air, no liquid water to draw from, no soil to grow food in without preparation, and no safe temperature by default. Life support therefore becomes a continuous process of regulation and recycling. For long journeys, the limiting question is not how to survive for a day or a week, but how to keep air, water, and nutrition reliable for months, years, or decades, while hardware ages and small failures accumulate. This need turns travel into an exercise in building a small, dependable world. Air management begins with oxygen and carbon dioxide. Humans consume oxygen and produce carbon dioxide through metabolism. In a sealed cabin, carbon dioxide would rise to dangerous levels quickly without removal. Spacecraft use chemical or physical systems to scrub carbon dioxide from the air and to replenish oxygen, either from stored supplies or by generating oxygen from water through electrolysis. Electrolysis splits water into hydrogen and oxygen using electricity. The oxygen is breathed while the hydrogen can be vented or combined with captured carbon dioxide in chemical processes that produce water and other byproducts. The degree of closure, meaning how much material is recycled rather than resupplied, determines mission endurance. A highly open system relying on stored oxygen and consumables becomes heavy and finite. A more closed system reduces resupply needs, but increases hardware complexity and the need for robust maintenance. Water is both a consumable and a tool. It is required for drinking, food preparation, hygiene, and in some cases as radiation shielding. Water can be recycled from humidity in the air and from urine and other waste streams. Modern spacecraft and stations already recycle a significant fraction of water, yet no system is perfect. Filters clog, microbes grow in plumbing, chemical balances drift. Over long durations, even small losses become large. A loss of a few % per month becomes untenable over years. Long missions therefore demand either near complete recycling or access to external water sources. Within the solar system, external sources might exist on the Moon, Mars, or icy bodies, but using them requires mining and purification infrastructure. During transit between worlds, the ship must rely on what it carries and what it can reclaim. Food supply is a major mass driver for long missions. Stored food can last years if processed and packaged properly, but variety, nutrition, and palatability become concerns. Vitamins degrade over time, especially in radiation-rich environments. Long storage also increases the risk of contamination and spoilage if packaging fails. Growing food on board could reduce stored mass and improve freshness, but it demands volume water lighting and careful control of microbes and nutrients. Plants also produce oxygen and absorb carbon dioxide, which can support air management. Yet running a stable onboard agriculture system for years is difficult. It turns a spacecraft into a biological laboratory where small imbalances can cascade. Soil is heavy and can harbour pathogens. Hydroponic systems require pumps and nutrient solutions. Lighting requires significant power. For very long missions, some form of food production may be necessary, but it increases complexity and the demand for skilled maintenance. Waste management links directly back into air and water cycles. Human waste contains water and nutrients, but also pathogens and chemicals that must be controlled. Waste processing must prevent contamination of air and surfaces, while extracting reusable water and possibly nutrients for plant growth. Microbial control is constant because a sealed habitat is an ideal place for microbes to spread. Spacecraft surfaces, air filters, and water lines can become colonized. In microgravity, fluids behave differently, and small droplets can float and spread contamination. Long missions therefore require strict hygiene systems, careful materials, and monitoring to detect microbial growth before it becomes harmful. Thermal control is another continuous need. Inside the habitat, heat is produced by bodies and electronics. Outside space is cold in the sense that there is no medium to carry heat away, yet sunlight can heat surfaces intensely. The habitat must keep a narrow temperature range for human comfort and equipment function. Because heat must be radiated away radiators, and heat loops are essential. If power increases for propulsion or for artificial lighting, heat rejection becomes harder. Thermal control systems must remain reliable for the entire journey. Leaks, pump failures, or radiator damage can threaten survival, even if air and water remain adequate. Pressure containment is fundamental. The habitat must maintain an internal pressure suitable for breathing, while withstanding the vacuum outside. Micrometeoroid impacts and debris can puncture hulls. Spacecraft use multi-layer structures and sometimes dedicated shielding to reduce puncture risk. For long missions, the probability of impact increases with time and with cross-sectional area. Repair capability becomes essential. The crew must be able to locate leaks, seal them, and reinforce damaged areas. This requires tools, spare materials, and training, adding mass but increasing resilience. Life support also includes medical stability. In deep space, immediate evacuation is impossible. The crew must manage injuries, infections, and chronic conditions with limited supplies. Radiation exposure can increase long-term cancer risk and may affect the nervous system and other organs over time. Microgravity affects immune function and wound healing. A long mission therefore requires careful crew selection, preventive care, and onboard medical equipment. Telemedicine support from Earth becomes limited by communication delay. Decision-making must be local. Medical capability adds mass and complexity, but without it, the acceptable mission duration shrinks. Psychological stability is part of life support because it affects performance and safety. Long confinement, monotony, and separation from Earth can produce stress-sleep disruption and interpersonal strain. Habitats must provide some degree of privacy, a stable day-night rhythm, meaningful work, and recreation. These needs shape interior volume and design. Increasing volume increases mass. The mass constraint therefore presses directly against mental health needs. The problem is not solved by discipline alone. It is solved by designing environments that support stable human function over long periods. The level of closure required grows with distance. A mission to the Moon can carry most consumables. A mission to Mars pushes toward extensive recycling and careful resource management. A mission lasting decades would require near-complete closure, where losses are extremely small, maintenance is routine, and spare parts can be manufactured or substituted. Manufacturing in space, such as using additive manufacturing, can reduce the need to carry every spare, but it requires feedstock material power and reliable machines. It also requires the ability to certify parts for safety-critical use. Over long time spans, even the availability of small replacement components can determine survival. The life support problem defines a practical boundary between exploration and settlement. If a crew can reach a destination but cannot resupply or establish a stable habitat upon arrival, then the journey becomes a one-time survival test rather than a sustained presence. Within the solar system, settlement may be possible at some locations if local resources can be used, especially water and oxygen-bearing materials. Beyond the solar system, there is no guarantee that a target system offers accessible resources, and reaching it would already demand extreme endurance. For interstellar travel, the spacecraft itself may need to function as a self-contained world for the full duration, with the ability to repair, recycle, and perhaps reproduce its population without external input. This moves the boundary of feasibility inward toward biology and systems engineering rather than propulsion alone. In this region, the constraints are no longer dominated by distance and speed, but by the stability of a closed habitat. The next inward step is to focus on one of the most persistent external threats to that habitat, and to the bodies inside it: radiation. Radiation is present everywhere in space, but it becomes more severe with time and with distance from Earth's protective environment. Understanding its sources and the limits of shielding is essential for judging the ultimate horizon of human travel. Radiation in space is not a single thing. It is a collection of energetic particles and photons that can penetrate materials, damage electronics, and alter living tissue. On Earth, the atmosphere and magnetic field reduce much of this radiation before it reaches the surface. In space, especially beyond low Earth orbit, that protection weakens or disappears. For long journeys, radiation becomes a cumulative constraint. It does not usually act as an immediate catastrophe, but as a steady addition of risk that grows with time. When the question is how far humans could ever travel, radiation links distance to biology, because longer trips and deeper destinations mean more exposure and fewer opportunities to shelter. One major source is solar energetic particles, bursts of protons, and heavier ions accelerated during solar flares and coronal mass ejections. These events can deliver high doses over hours or days. The timing is irregular. Some solar cycles are more active than others, and even within a cycle, storms are unpredictable on the timescale of a crewed mission. A spacecraft traveling to Mars or beyond must therefore be prepared for sudden radiation events that could exceed safe limits if no shelter is available. The most practical defense is a storm shelter, a region of the spacecraft with extra shielding, often using water food stores and other mass that is already needed. During an event, the crew stays there until the intensity falls. This approach can reduce acute risk, but it increases spacecraft mass and requires careful interior layout. Another major source is galactic cosmic rays. These are high-energy particles, mostly protons, but also heavier nuclei, arriving from outside the solar system, likely accelerated by supernova remnants and other energetic astrophysical processes. Cosmic rays are present continuously. Their energies can be so high that they penetrate substantial shielding. When they strike shielding or tissue, they can produce secondary particles, including neutrons that add to exposure. Unlike solar energetic particles, cosmic rays are difficult to block completely with practical spacecraft mass. Adding more shielding does not always reduce risk proportionally because of secondary radiation production. The best shielding materials for cosmic rays tend to be rich in light elements, such as hydrogen, which reduces secondary particle production compared with dense metals. Water and certain plastics can therefore be effective, yet the thickness required to significantly reduce exposure still adds large mass. Radiation effects on the human body include damage to DNA, increased cancer, risk potential effects on the central nervous system, and impacts on the cardiovascular system. The body can repair some damage, but not all. Risk accumulates with total dose and depends on the type of radiation. High-energy heavy ions, a component of cosmic rays, can cause dense tracts of ionization through tissue, which may be more biologically damaging than lower-energy radiation. The uncertainty in precisely quantifying long-term health outcomes is acknowledged in space medicine, but the overall direction is clear. Longer exposure increases risk, and deep space exposure is higher than exposure in low Earth orbit. Within low Earth orbit, Earth's magnetic field deflects many charged particles. The International Space Station still experiences radiation, but it is partially shielded by the magnetosphere and the residual atmosphere below. Beyond that region in cislunar space and interplanetary space, protection drops. On the way to Mars, for example, a crew spends months in a region where cosmic rays are largely unshielded by Earth's field. Mars itself has a thin atmosphere and localized magnetic fields but lacks a strong global magnetosphere like Earth's. Its surface offers some shielding, especially if habitats are placed under regolith or within natural formations, but during transit the spacecraft must provide protection. The radiation environment also varies with the solar cycle. Cosmic ray intensity near Earth tends to be higher during periods of low solar activity, because the solar wind and magnetic field are weaker at deflecting incoming galactic particles. During high solar activity, cosmic ray intensity can be lower, but solar energetic particle events can be more frequent and intense. This creates a trade. Launching during a certain phase may reduce one type of risk while increasing another. Mission planners can choose windows to balance this, but they cannot remove the uncertainty. A long mission will likely experience a range of conditions. Radiation also affects electronics and materials. High-energy particles can flip bits in memory damage sensors and degrade solar panels. Over years, this can reduce spacecraft capability. Redundancy and error correction can manage some of these effects, but they add complexity and power use. For long missions, radiation hardening becomes essential. This is another way radiation couples to mass and energy. More shielding and more robust systems increase mass, which makes propulsion harder. If a mission aims for higher speeds to reduce travel time, and therefore radiation exposure duration, it may enter regimes where collisions and relativistic effects increase hazards. The constraints remain entangled. Shielding strategies involve geometry as much as material. A spacecraft can place heavy stores such as water tanks around sleeping areas and storm shelters. It can arrange equipment to serve double duty as shielding. It can minimize exposed surface area for a given internal volume, though crew comfort often pushes toward larger habitable volume. Some concepts propose magnetic or electrostatic shielding to deflect charged particles mimicking Earth's magnetosphere. In principle, fields can deflect particles, but generating strong large fields requires significant power and mass, and some particles, especially high-energy cosmic rays, are difficult to deflect without enormous field strengths. Moreover, fields can introduce new risks by trapping particles or interfering with equipment. As of current evidence, passive shielding combined with operational strategies remains the more grounded approach for near-term missions. Radiation is also tied to destination choice. Travel within the inner solar system remains within the realm, where mission durations can be limited, and where sunlight provides power for life support systems, reducing reliance on heavy nuclear sources. Missions to the outer solar system require longer transits, often years, increasing cumulative cosmic ray exposure. They also operate in regions where sunlight is weak, encouraging nuclear power sources which introduce their own shielding and heat management requirements. In addition, some destinations, such as the regions near Jupiter, have intense trapped radiation belts that can deliver severe doses quickly. Robotic missions manage this by limiting time in high radiation zones and using radiation-hardened electronics. Humans would require heavy shielding and careful trajectory design, likely making sustained presence near such belts extremely challenging. The existence of safe havens within a spacecraft becomes central. A crew travelling for months must sleep, work and exercise, but they may need to retreat periodically to better shielded areas during solar events. Over longer missions, the cumulative time spent in shelters could be significant. The internal architecture of the ship therefore matters for health. It must allow normal living while providing rapid access to high shielding regions. This again adds mass and volume linking radiation protection back to the mass constraint of propulsion and launch. Over interstellar distances, radiation remains present. Cosmic rays permeate the galaxy. A long interstellar voyage would involve many years or decades of exposure. Even if the ship travels fast and time dilation reduces the crew's experienced time in the Earth frame, the ship still traverses vast distances, and in the ship frame, high-speed motion can transform the radiation field, shifting energies and directions. Managing radiation over such timescales likely requires heavy shielding and perhaps active systems not yet demonstrated. The problem does not scale gently. It grows with the ambition of the journey. Radiation therefore sets one of the most practical boundaries for human reach. It is not always the first obstacle to be encountered, but it is persistent, cumulative, and difficult to engineer away without adding mass. It pushes realistic human missions toward shorter durations and toward destinations where shelter and local shielding can be established. This naturally favours nearer targets such as the Moon and Mars, where transit times are limited, and where surface habitats could be shielded by local materials. The next inward step is to consider another continuous environmental condition that shapes human capability in space, the absence of gravity as felt on Earth. Microgravity is not merely a comfort issue. It changes bones, muscles, fluids, and sensory systems. Over long durations, it can become a limiting factor as direct as radiation, and it interacts with spacecraft design, mass, and energy. In space, the body lives in a condition that is not natural for its long-term design. Microgravity, meaning the near weightlessness of free fall, removes the constant load that bones and muscles experience on Earth. The body adapts quickly, and adaptation is not always beneficial. Over days, fluids shift toward the head. Over weeks and months, muscles weaken, and bones lose mineral density. The heart and blood vessels adjust to a different pattern of work. The inner ear and balance system tuned for gravity must recalibrate. For short missions, these changes are manageable. For long missions, they become a central constraint on how far humans can travel while remaining healthy and capable. Bone loss is one of the most documented effects. On Earth, bones maintain strength through continual remodeling, adding and removing tissue in response to stress. In microgravity, the stress on weight-bearing bones is reduced, and the body reduces bone formation while increasing bone resorption in certain regions. This can lead to measurable loss of bone mineral density, particularly in the hips and spine. The loss increases fracture risk and may not fully reverse after return to Earth. Exercise and nutrition can reduce loss, but they do not eliminate it entirely. Over journeys lasting many months, the cumulative impact becomes significant. A crew arriving at a destination may face reduced strength and a higher risk of injury during demanding operations such as landing surface work or emergency repairs. Muscle loss follows a similar pattern. Muscles maintain mass and strength through regular use against resistance. In microgravity, many postural muscles are used less, and overall mechanical loading drops. Without countermeasures, muscle atrophy occurs particularly in the legs and back. Exercise regimes on space stations use resistive devices and aerobic equipment to provide loading and maintain cardiovascular fitness. These countermeasures require time each day, reliable equipment, and sufficient space. On long missions, equipment must be maintained and repaired without resupply. This again ties human physiology to spacecraft mass and design. A vehicle that is too small or too lightly equipped may save propellant but produce a crew that is physically compromised. Fluid shifts toward the head affect the cardiovascular system and can contribute to changes in vision. In microgravity, blood and other fluids redistribute, increasing pressure in the upper body. Over time, the body adjusts by reducing overall blood volume. When astronauts return to gravity, this reduced volume can cause dizziness or fainting upon standing, known as orthostatic intolerance. For a crew arriving at a planet, the first hours and days in gravity may be physically challenging. If the destination gravity is lower than Earth, such as on Mars, the challenge may be reduced but not removed. The body will still face a transition, and operational planning must account for reduced capability during initial adaptation. Vision changes observed in long-duration spaceflight suggest that microgravity can alter pressure relationships in the head and eyes, affecting the shape of the eye and leading to changes in visual acuity. The exact mechanisms are still being investigated and individual susceptibility varies. This uncertainty matters because vision is critical for piloting monitoring instruments and performing repairs. If a long mission increases the risk of vision impairment, then mission duration and crew selection become constrained. Monitoring and mitigation strategies require medical equipment and expertise, adding to onboard demands. The immune system also appears to change in space. Stress-altered sleep radiation exposure and microgravity can influence immune function, potentially increasing susceptibility to infection or altering responses to latent viruses. In a closed habitat, microbes circulate among crew and surfaces. Even if a spacecraft begins clean, it carries human-associated microbes that can grow in niches. Changes in immune function therefore increase the importance of hygiene monitoring and medical capability. Over long durations, this becomes another layer of risk that grows with time. Sleep and circadian rhythms are influenced by the environment. In orbit, a spacecraft may experience multiple sunrises per day, and without careful lighting design and scheduling, the crew's internal clocks can drift. Poor sleep impairs cognition, mood, and performance. For deep space missions, maintaining a stable day-night cycle requires controlled lighting, predictable routines, and careful management of noise and workload. These are design and operational needs that compete with mass and power constraints. Good lighting systems require power and reliable components. Crew comfort requires volume and sound control. Long missions require an environment that supports stable mental function, not just survival. Psychological and social factors interact with physical ones. Exercise is essential for physiology, but it also supports mental health. Privacy supports mental health, but often requires space and careful layout. Communication delay increases isolation and reduces real-time support from Earth. The crew must therefore have autonomy and strong internal cohesion. Training must prepare for extended periods without immediate external advice. The habitat must support both teamwork and individual recovery. These requirements influence mission architecture as directly as propulsion does, because they determine what size and complexity of vehicle is necessary to keep humans functional. One proposed way to address microgravity is artificial gravity through rotation. If a habitat rotates, centrifugal acceleration can mimic gravity at the outer rim. This could reduce bone and muscle loss and stabilize fluid distribution. The physics is straightforward, but engineering and human factors are challenging. A rotating structure must be balanced and stable. Docking and propulsion become more complex if rotation is continuous. If rotation is slow, the required radius to avoid motion sickness becomes large, increasing structural mass. If rotation is fast, many people experience discomfort due to the way the inner ear senses rotation. A practical artificial gravity system would need careful design and testing. None has yet been used for human deep space missions. It remains a plausible but unproven countermeasure. Another approach is to accept microgravity during transit and plan for rehabilitation at arrival. This could work for missions where arrival operations can be delayed while the crew adapts. Yet some missions require immediate action, such as piloting landers, responding to systems failures, or constructing shelters. The ability to delay is not guaranteed. Furthermore, rehabilitation requires equipment and time which must be provided at the destination. If the destination is hostile and resources are limited, the margin for reduced capability may be small. For travel farther than Mars, the time spent in microgravity grows, and with it the risk. Even if propulsion could shorten travel time, higher speeds bring other hazards. A slow mission faces prolonged physiological decline. A fast mission faces energy and shielding challenges. This balance again shapes the practical horizon of human travel. It suggests that the most realistic near-term deep space human missions aim for durations on the order of months rather than many years, and they prioritize destinations where surface gravity and shelter can support recovery and long-term living. Microgravity therefore functions as another boundary that is not purely physical distance. It is an inward constraint rooted in biology that grows with time and interacts with vehicle design. It helps explain why human reach expands slowly compared with robotic reach. Machines do not lose bone density. They do not need exercise. They do not suffer from isolation in the same way. Human missions must carry the conditions for human health. The next inward step is to leave the solar system's familiar environment and consider the medium between stars. Even if a crew could remain healthy, and even if radiation could be managed, interstellar space introduces a new form of hazard that becomes important at higher speeds: the thin but real presence of gas and dust. These particles set limits on safe velocity and on shielding requirements, shaping the practical distance humans might ever cross. Between the stars, space is not truly empty. It contains a thin mixture of gas, mostly hydrogen and helium, and a sparse population of dust grains made of heavier elements, carbon-rich compounds and silicates. This interstellar medium is far less dense than any atmosphere, yet over large distances it becomes a persistent environment that a fast-moving vehicle must cross. At low speeds, the medium is almost irrelevant. At high speeds, it becomes one of the most serious hazards, because kinetic energy grows with the square of speed, and because impacts occur continuously. For human travel beyond the solar system, the interstellar medium defines a practical speed ceiling long before the theoretical light speed limit is reached. Interstellar gas densities vary by region. In some areas there are only a few atoms per cubic centimetre, while in denser clouds there can be many more. Dust is rarer than gas, but carries far more mass per particle. Dust grains range in size from tiny molecules to particles comparable to smoke or fine sand. Most grains are extremely small, yet even tiny grains can be destructive at high relative speed. The hazard is not that the ship will be shredded by a constant hail. The hazard is that occasional impacts at very high energy can cause severe localized damage, and that continuous bombardment by gas atoms can erode surfaces and generate radiation through secondary interactions. The relative speed between a spacecraft and the interstellar medium depends on both the spacecraft's speed and the motion of the local gas and dust. For a vehicle travelling at a small fraction of light speed, a dust grain impact can release energy comparable to an explosive at the point of contact. The exact effects depend on grain mass composition and impact angle, but the basic scaling is unforgiving. Increasing speed by a factor of 2 increases impact energy by a factor of 4. This quickly turns the sparse interstellar medium into a practical wall. Shielding can reduce risk, but shielding adds mass and introduces its own difficulties. A simple thick wall can stop small particles, but at high speeds, the impact can vaporize both the particle and part of the shield, creating a plasma and a spray of fragments that continue inward. Multi-layer shielding, where an outer layer breaks up the particle and an inner layer absorbs the debris, can reduce penetration risk. Such shielding is used on spacecraft for micrometeoroids. For interstellar speeds, the required thickness and spacing could become large, especially for a habitat-sized vehicle. The mass penalty would be severe, tying this problem back to propulsion and launch constraints. Another approach is to place a sacrificial shield in front of the craft, a thick block of material that slowly erodes but protects the main structure. Water or ice could serve as such a material, and it has the added advantage of being useful for life support. A forward tank of water could absorb impacts and also provide radiation shielding. Over time, however, erosion would consume the material, and the quantity required for long trips at high speed could be enormous. The shield would also need to be kept stable and integrated with the vehicle's structure and thermal control. If the shield is too large, it increases cross-sectional area, which increases the chance of encountering larger dust grains. The design becomes a balancing act between protection and exposure. Detecting dust grains ahead of the craft is difficult. Dust is small and reflects little light. At high speeds, the time between detection and impact is short. If a craft travels at a significant fraction of light speed, even a grain detected thousands of kilometers ahead would be only seconds away. Maneuvering a large vehicle to avoid such a grain would require high lateral acceleration and precise control, and it would likely be impractical for anything but the smallest craft. For a large crewed ship, avoidance is therefore not a reliable primary defense. The ship must assume it will collide with many particles and must be designed to endure it. The interstellar medium also interacts with the ship through heating. A fast craft ploughs into a thin gas, converting some kinetic energy into heat and radiation at the leading surfaces. At modest speeds, this is negligible. At high speeds, it can become a significant power input that must be managed by the thermal control system. The leading edge may need to withstand continual heating and sputtering where atoms are knocked out of the surface by impacts. Materials must resist erosion and maintain structural integrity. This is a long-term wear problem where the duration of the mission matters as much as speed. The medium can also become a source of radiation through secondary particle production. When high-energy impacts occur, they can generate showers of particles and high-energy photons. These can penetrate deeper into the spacecraft and contribute to crew exposure. Shielding against this overlaps with shielding against cosmic rays, but the directionality becomes more pronounced with the highest hazard coming from the forward direction. This suggests a ship layout with the most protected areas placed deep behind the forward shield and with sensitive equipment and habitats arranged to minimize direct line of sight to the leading surface. Such layout choices influence internal architecture and mass distribution. Another feature of interstellar travel is navigation through a medium that is not uniform. There are regions of denser gas regions with more dust and regions influenced by stellar winds from nearby stars. A route through interstellar space could in principle be chosen to avoid denser clouds, reducing impact rates. Yet mapping the small-scale distribution of dust and gas along a path many light-years long is challenging. Remote observations provide averages and broad structures, but not the fine-grained distribution that matters for high-speed safety. Uncertainty remains, and uncertainty must be met with engineering margin. Engineering margin adds mass. For uncrewed probes, the interstellar medium can be addressed with small cross-sectional area and robust forward shielding, accepting the possibility of mission loss. For humans, acceptable risk is much lower, and the vehicle must maintain pressure integrity and life support function. A single puncture that cannot be repaired could be fatal. Thus, the interstellar medium becomes a stronger constraint for human travel than for robotic travel. It reinforces the idea that machines will go farther and faster first, exploring conditions and testing shielding concepts before any human attempt. These hazards imply that human interstellar travel, if it occurs, may be constrained to relatively low cruising speeds compared with some speculative concepts. Lower speed reduces impact energy dramatically and reduces heating and secondary radiation. The cost is time. Time then collides with life support and biology constraints. The ship must function for longer, and the crew must remain healthy for longer. This is the central tension of human interstellar travel. Speed is dangerous because of the medium, and slowness is dangerous because of duration. Some proposed strategies attempt to soften this tension by using very fast but very small craft, or by using remote habitats and pre-built shelters at the destination. Yet pre-building shelters at another star requires sending machines first, which returns the problem to robotic travel. For humans to follow the interstellar medium remains a corridor that must be crossed safely. The interstellar medium also shapes expectations about how far could be reached within a given technological era. If a civilization can build a slow, heavily shielded ship, it may reach the nearest stars in centuries functioning as a generational habitat. If it can build a faster ship, it must confront the medium as a serious hazard, and must develop materials and shielding architectures that can withstand repeated impacts at high energy. Both pathways demand capabilities beyond current human practice. The medium therefore acts as a practical filter on all interstellar ambitions. Having entered the space between stars, the next inward step is to consider what machines already demonstrate about reaching outward. Uncrewed probes provide real examples of spacecraft that leave the solar system and operate for decades. Their speeds, power systems, and endurance offer a baseline for what is proven, and they clarify the difference between what can be imagined and what has actually been done. Human reach into space is often measured by where machines have already gone, because machines are the first travellers into every new region. They carry instruments instead of habitats. They can endure cold radiation and long silence. They can function with limited power and without food or air. By observing what uncrewed probes achieve, a practical baseline emerges for distance, speed, and longevity in real engineering. This baseline does not define the ultimate limit, but it shows what is feasible with known propulsion, known power systems, and known materials. The farthest human-made objects are deep space probes launched in the 20th century that continue to move outward from the Sun. Their trajectories are shaped by gravity assists and by the initial energy provided by chemical rockets. Once their propulsive phases ended, they became coasting travellers, carrying their initial momentum through the outer solar system and into interstellar space. Their speeds are a small fraction of light speed, yet over decades they traverse tens of billions of kilometres. Their existence demonstrates that spacecraft can survive for very long times in deep space if designed for reliability and if power remains available. Power is the central factor for long-duration probes. Solar panels work well near the Sun but become less effective with distance, because sunlight weakens with the square of distance. For probes sent to the outer solar system, radioisotope power systems have provided steady electricity for decades, using the heat from radioactive decay to generate power. These systems produce limited power, so instruments and communications must operate sparingly. Over time, power output declines as the radioisotope decays and as thermoelectric components degrade. This gradual decline places an operational horizon on missions. A probe may still be alive and drifting, but its ability to transmit data can fade. For human travel, similar constraints apply in different form. A crewed vehicle needs far more power than a probe, and it must maintain power for life support continuously, not only for occasional transmissions. Communications illustrate the reality of distance. As probes move farther away, their signals weaken and their data rates drop. Large antennas and sensitive receivers on Earth are required to detect and decode the transmissions. Commands sent outward take hours to arrive, and replies take hours to return. Even within the solar system, communication delay becomes a defining operational feature. For interstellar distances, the delay becomes years, and a crewed ship would operate with near total autonomy. The probe experience shows that autonomy can work for machines, but it also shows that human-controlled real-time operations do not scale outward. The endurance of probes also reveals the importance of simplicity. Long-lived spacecraft tend to be built with robust redundant components and with conservative operating margins. They avoid excessive mechanical complexity that could fail over time. Where moving parts are necessary, such as for pointing antennas, they are designed for long life and limited use. Thermal control is often passive where possible. These design principles support longevity but can limit performance. For example, a probe may not have high-thrust propulsion for course changes later in its life, because carrying such capability would add mass and complexity. This illustrates a recurring theme: capability and endurance trade against each other. A human ship would need both high capability and long endurance, a combination that increases mass and complexity dramatically. The speeds achieved by existing probes are instructive. Even after gravity assists, their outward speeds are measured in tens of kilometers per second. This is fast by human standards, but slow by interstellar standards. At such speeds, reaching the nearest star would take tens of thousands of years. These numbers highlight the difference between leaving the solar system and reaching another star. Leaving the solar system is a milestone, but not a gateway to interstellar travel in practical time. It shows that the boundary of the sun's immediate influence can be crossed, but it does not close the gap to the stars. Some modern probe concepts aim to increase speed through improved propulsion or through beamed energy. Light sail concepts, for example, could in principle accelerate small payloads to a few percent of light speed if pushed by powerful Earth or space-based lasers. Such concepts are technically demanding and remain developmental, but they illustrate a plausible path for robotic interstellar precursors. A small probe can be accelerated quickly because its mass is tiny. It does not need thick shielding for humans. It does not need a closed habitat, and it can accept higher risk. It can also accept a flyby encounter, collecting data during a brief passage. This is a radically different mission type from human travel, which requires arrival with control and long-term survival. Robotic probes also provide lessons about the space environment. They have measured dust densities, plasma conditions, magnetic fields, and radiation levels across the solar system. They have encountered micrometeoroid impact solar storms and component degradation. Each dataset helps constrain the unknowns that would matter for human travel. Yet probes have limitations. They sample a narrow path and a specific era. The interstellar medium varies and the sun's activity varies. Probes provide partial maps, not complete guarantees. Still, they are the only direct evidence available for many regions, and they guide realistic expectations. The boundary between robotic and human travel becomes especially clear when considering repair and maintenance. A probe can fail and still be a success if it transmits enough data before the failure. A human habitat cannot treat failure that way. Life support must be continuous. Systems must be repairable. Power must be steady. Consumables must be managed precisely. The design philosophy changes from maximizing scientific return per kilogram to maximizing survival per kilogram. This shift tends to increase mass and reduce attainable speed and distance for a given launch capability. Robotic missions also demonstrate the value of prepositioning and staging. Landers and rovers can be sent to Mars ahead of humans. Supplies can be cached. Communication relays can be placed in orbit. Within the solar system, these methods can create a scaffold that makes human missions safer. This suggests a likely pathway for human expansion machines build the infrastructure, and humans follow into an increasingly prepared environment. The farther outward the ambition, the more extensive the robotic preparation must be. For the Moon and Mars, such preparation is difficult but conceivable. For other star systems, it becomes a multi-century project even for machines, unless very fast robotic travel becomes practical. The probe record therefore sets a grounded horizon. With current propulsion, machines can traverse the solar system and exit it, operating for decades. With modest improvements and with nuclear power, they can explore more extensively. With advanced beamed propulsion, small robotic payloads might reach nearby stars within decades of travel time, though this remains a challenging engineering frontier. Humans, however, cannot simply scale up these achievements, because the added mass and fragility of a living system changes the equation. This does not mean humans cannot travel farther than probes. It means that the path to doing so likely involves creating habitats that function as independent worlds, and developing propulsion and shielding solutions that are safe over long time spans. The most plausible human pathway to interstellar distances is therefore not a single leap, but a gradual outward extension supported by robotic exploration and infrastructure. The next inward step is to consider how human missions might cope with the long times implied by modest speeds. If speed cannot be pushed high without severe hazards, then duration must be accepted. This brings forward the concept of multi-generation travel and other time-stretching approaches that remain within known physical limits, while confronting the biological and social constraints already described. If human travel cannot rely on extreme speed, then it must rely on endurance across long spans of time. This is the central dilemma of reaching other stars with known physics. A crewed ship travelling at speeds comparable to current probes would take thousands of years to reach even the nearest stars. Increasing speed to a small fraction of a light speed reduces travel time to centuries or decades, but doing so demands energy and shielding burdens that grow rapidly. When these burdens remain too high, the only remaining variable is duration. This turns the idea of travel into the idea of a moving habitat that persists across generations. A multi-generation mission is not a single expedition in the usual sense. It is a long-term community living inside a spacecraft where the people who launch are not the same people who arrive. The ship must sustain reproduction, childhood development, education, social stability, and long-term governance while also maintaining life support, propulsion, and repair capability. The biological requirements of pregnancy, infant care, and child health introduce new constraints beyond those of an adult crew. The habitat must provide adequate nutrition, medical care, and space for growth. It must manage radiation exposure carefully because developing tissues are more sensitive. It must provide a stable environment over decades, not only physically but psychologically. These needs expand the mass and complexity of the ship, increasing the propulsion challenge and reinforcing the slow speed requirement that created the generational concept in the first place. The closed life support system for a generational mission must operate with extremely low loss rates. Small leaks of air or water that are acceptable over months become fatal over centuries. Recycling systems must be maintainable with locally available materials. This implies onboard manufacturing and a supply of raw feedstock that can be turned into replacement parts. It also implies detailed knowledge transfer across generations, so that future crews understand how to maintain systems they did not build. The ship becomes a technical culture as much as a physical craft. Without reliable education and institutional memory, complex systems degrade and fail. Microgravity and radiation concerns also deepen on a generational timescale. If the ship does not provide artificial gravity, then children may grow in microgravity, and the long-term effects on development are not well established. Bone growth, muscle development, vestibular function, and cardiovascular development might differ in a low-gravity environment. A generational mission therefore benefits strongly from artificial gravity. Yet providing artificial gravity through rotation tends to require a large radius to keep rotation rates comfortable. A larger structure increases mass and surface area, increasing the challenge of shielding and impact protection. It also increases the probability of micrometeoroid damage over long durations. The ship must be robust and repairable at scale. Social stability becomes a limiting factor as direct as any physical constraint. A small population risks inbreeding and loss of genetic diversity. A larger population reduces genetic risk but demands more space, more food production, more water processing, and more power. It also demands stronger social systems to manage conflict and maintain cooperation. The ship cannot rely on rapid external intervention. Communication with Earth would eventually become delayed by years and then by centuries if the mission continues outward. For practical purposes, the ship becomes an independent society. Maintaining a stable cooperative society for centuries is a profound challenge. It is not a matter of will alone. It requires robust cultural and institutional design which cannot be tested fully except by living it. Another endurance approach sometimes discussed is metabolic reduction, where humans are kept in a state of greatly reduced activity to slow aging and reduce consumable needs. In some animals, torpor and hibernation occur naturally. For humans, no proven safe method exists to induce long-term hibernation-like states for years. Short-term medical cooling and sedation are used in specific contexts on Earth, but extending these methods to long-duration spaceflight introduces risks of muscle loss, immune suppression, blood clots, and neurological effects. It also does not remove radiation exposure. A dormant body still accumulates, dose and repair processes may be reduced. Without a demonstrated technology, metabolic reduction remains speculative as an operational solution. It cannot be treated as a reliable pathway for human reach. A related approach is to avoid carrying a full adult crew for the entire journey by sending stored genetic material and embryos, or by sending automated systems that can create and raise humans at the destination. This concept shifts the problem from crew endurance to the reliability of robotics and artificial care over decades. It also raises complex biological and developmental uncertainties. Human development depends on environmental conditions, social interaction, and stable care. Creating that autonomously in a distant system without human oversight is beyond current capability. In practical terms, it replaces one set of difficult constraints with another, and does not remove the need for a stable habitat. These endurance approaches share a common requirement: the ship must be a durable world. It must have layers of redundancy, the ability to repair major structural damage, and the ability to adapt to gradual degradation of materials. Metals fatigue, polymers degrade under radiation, seals harden and crack, electronics suffer cumulative damage. Over centuries, even well-designed components will fail. The ship must therefore carry not only spare parts, but the capability to produce new parts. This implies machine tools, fabrication systems, and quality control methods. It implies stored knowledge and the ability to measure and test materials. The ship becomes less like a vehicle and more like a mobile industrial base. The interstellar medium and dust hazard also becomes more relevant over long durations. Even at modest speeds, small impacts accumulate. The ship must continuously maintain its outer layers. If it travels faster to reduce duration, the energy of impacts rises, demanding thicker shielding and more frequent repair. If it travels slower, impacts are less energetic, but the exposure time is longer. Over centuries, even low impact rates can produce significant erosion. The best balance depends on the actual dust environment along the route, which may not be fully known. Engineering must therefore be conservative, increasing mass. These realities suggest that the farthest human travel within known physics is likely not a quick dash to another star, but a slow migration, supported by extensive infrastructure and by acceptance of long timescales. Such missions might be conceived less as travel and more as relocation, where the ship is the primary habitat and the destination is a new region for settlement rather than a site for brief exploration. Yet even under this framing, the requirements are enormous. The ship must be built, launched and sustained, and the initiating civilization must invest resources for outcomes it will not witness. Within the solar system, many of these challenges can be reduced by using destinations with resources. A long-term settlement on Mars or on a large asteroid could develop industry produce propellant and build larger structures in space without lifting everything from Earth. Over centuries, such a spacefaring civilization could in principle accumulate the capability to assemble a generational ship. This points toward an outer to inner pathway of development, first near-Earth operations, then sustained habitats on nearby worlds, then larger industrial capacity in space, and only then the possibility of interstellar habitation. The inward focus now returns to the central question of practical horizons. With the physical limits of light energy, mass radiation biology, and the interstellar medium in view, a boundary emerges that is less about absolute possibility and more about what is likely achievable and sustainable. The final section draws these constraints together to describe the most realistic outer edge of human reach through space under known physics and plausible engineering growth, without claiming certainty where evidence is incomplete. The farthest humans could ever travel through space is not a single distance. It is a set of horizons defined by different clocks and different constraints. One horizon is the distance reachable by individuals within a lifetime, using vehicles that can be built and operated with high reliability. Another horizon is the distance reachable by human societies willing to sustain missions across generations, accepting that the travellers and the departure world will diverge. A third horizon is set by the expanding universe itself, where many regions are permanently beyond reach, regardless of technology, because space expands in a way that carries them away faster than light can connect. Across all horizons, the same limits recur: the light speed boundary, the rising energy cost of high speed, the compounding mass penalty of propellant and shielding, the biological requirements of life support, and the persistent hazards of radiation and the interstellar medium. Within the nearest horizon, the solar system remains the most plausible arena for sustained human travel and settlement. The Moon and Mars are reachable with known propulsion, and can support staged development of habitats and resource use. These destinations allow learning how to close life support loops, manage radiation with local shielding, and build infrastructure beyond Earth. They also allow gradual reduction of dependence on Earth by extracting water, oxygen-bearing materials, and construction resources. As infrastructure grows, the effective reach of humans within the solar system expands, not by breaking physics, but by reducing the cost of mass and by improving reliability. Human travel to other near-Earth bodies and possibly to some asteroids becomes more practical when propellant depots, construction facilities, and repair capability exist away from Earth. In this near horizon, the limiting factors are largely economic and engineering rather than fundamental physics, though radiation and microgravity remain persistent constraints. The next horizon beyond routine solar system travel is where interstellar distances begin. Here the problem changes character. The distance to the nearest stars is only a few light years, yet even that is enormous compared with the scale of planetary travel. To reach another star within a human lifetime as measured on board would require speeds close enough to light speed that energy demand shielding and impact hazards become extreme for a crude habitat. Time dilation can reduce the traveller's experienced time, but it does not reduce the energy required to accelerate mass to such speeds, nor does it remove the need to protect the crew from dust impacts and radiation. In the Earth frame, the journey still takes at least the light travel time, and for practical speeds it takes longer. Thus, the lifetime-scale interstellar horizon depends on breakthroughs in power density materials and shielding architecture that are not yet demonstrated. It remains physically permitted in principle, but bounded by severe practical hurdles. A more conservative interstellar horizon is the generational one. If a ship travels at modest speeds, perhaps a small fraction of light speed or less, the interstellar medium becomes less violent, and shielding demands become more manageable. Yet travel time stretches to centuries. In this regime, the ship must function as a durable habitat and an industrial system. It must recycle air and water with near-complete efficiency, produce food, reliably manage microbial ecology, and maintain thermal control and structural integrity. It must repair itself and replace failing components using onboard manufacturing. It must maintain a stable human population with adequate genetic diversity and social resilience. These requirements are not forbidden by physics, but they are vast in engineering and organizational scope. The most realistic path to such capability likely involves long development within the solar system, where failures can be studied and infrastructure can be supported. If such ships are ever built, their destination choices would likely prioritize nearby stellar systems, because each additional light year adds years or decades and compounds risk. In practical terms, the generational horizon might extend to the closest stars and perhaps to a limited neighborhood of stellar systems within a few tens of light years, depending on achievable speed and ship resilience. Beyond that local neighborhood, even generational travel faces compounding constraints. A ship that must operate for many centuries experiences cumulative material degradation, cumulative radiation exposure, and cumulative probability of rare but severe failures. Even if the population remains stable, the ship's outer layers face continual erosion and occasional impacts. The long duration also increases the chance that the destination system changes in ways that affect arrival plans, such as shifts in stellar activity or the availability of accessible resources. While stars evolve slowly on the timescale of centuries, local conditions such as dust environments and planetary configurations can still matter. The longer the travel, the more unknowns accumulate. This does not create a sharp boundary, but it suggests diminishing returns as distance grows. A separate horizon is set by the reachable universe under cosmic expansion. Even if humans could travel at speeds close to light for very long times, many galaxies are already receding in such a way that they cannot be reached. The expansion of space creates an event horizon beyond which a traveler limited by light speed cannot ever arrive. Within the Milky Way and the local group gravity bind structures together, so expansion is not the primary factor. But on larger scales, expansion limits reach. Over cosmic time, more of the observable universe becomes unreachable, as distant galaxies cross the threshold where their recession through expanding space outpaces any light speed travel from here. This means the ultimate boundary for travel is not the edge of what can be seen today, but a smaller and shrinking region of gravitationally connected space. Within the Milky Way itself, another practical horizon appears. The galaxy is vast, and reaching far regions would require travel times that are long even at ambitious speeds. A near-light ship could in principle traverse large galactic distances within a human lifetime, as measured on board, but only by paying the extreme energy and shielding costs already described. A slower, safer ship would require many thousands of years. This suggests that most realistic human expansion, even in a far future scenario, would concentrate in a limited volume around the original home system and any early settlement systems, rather than spreading quickly across the entire galaxy. Machines might map and explore widely, but human habitation would likely remain clustered where travel and support are practical. The practical horizon for how far humans could ever travel is therefore likely to be set by a combination of sustainable infrastructure and tolerable risk rather than by a single absolute law. Within the solar system, sustained travel and settlement are plausible with continued development. To nearby stars, human travel is physically possible, but would require either extreme speed vehicles with heavy shielding and immense energy, or slow generational habitats with deep self-sufficiency. Beyond a local stellar neighborhood, the compounding burdens of time maintenance and uncertainty grow so large that human travel becomes less likely, even if robotic exploration continues outward. Beyond the event horizon defined by cosmic expansion, travel is not possible at all within known physics regardless of effort. These boundaries do not end curiosity or exploration. They describe the shape of what can be reached by living bodies that must breathe, eat, and remain healthy while crossing an environment that offers little mercy. The universe provides many destinations, but it also imposes costs that scale steeply with ambition. The most robust path for humans is likely to extend reach step by step, building stable habitats and industrial capacity close to home, learning to manage life support and radiation for long periods, and letting machines probe the farthest distances where humans are least suited to go. After the farthest horizons are described, the pace settles and the scene remains with what is immediate and stable. The solar system continues to move in quiet regularity. Earth circles the Sun, and the Moon circles Earth, following paths that can be predicted with precision. Within this near region, human travel is shaped by reachable distances measured in days and months, by engines that can be tested and repaired, and by shelters that can be built with materials that can be touched and weighed. Farther out, the distances grow and the rules do not change, but the consequences become heavier. Time stretches. Communication delays widen. Systems must endure without interruption. The hazards of radiation and impact remain present, not dramatic, but persistent, like a steady background condition. Every additional year of travel adds exposure, and adds the chance that something small becomes something serious. The body adapts to weightlessness, and the adaptation has costs that must be counted every day. Air and water cycles must remain clean and balanced, and the heat of machines must still be carried away by radiators into the dark. Beyond the solar system, the space between stars stays thin but not empty, and speed turns that thinness into force. These are quiet facts that do not change with desire. They frame what travel can be. They also frame what can be built with patience, more reliable systems, better recycling, stronger materials and habitats that support health for longer periods. The outer distances remain vast, yet the inner requirements remain constant. A living crew needs stable air, stable water, stable food, stable temperature, and the ability to rest and work in a confined place. When those needs are met, travel can extend outward in careful steps. When they are not met, distance becomes irrelevant because survival narrows the world to the volume of a single ship. In the long view, the reachable space for humans is the space that can be made stable, where risk is reduced by preparation rather than speed, and where the journey is paced by what can be sustained. The sky stays full of light from distant places arriving after long travel through time. For human travellers, the calm path outward remains tied to the slow work of building safe environments and to the steady acceptance of limits that are already written into the structure of space itself.